Unit 4, Lesson 7. Here we go. We are talking about the number of solutions that any equation can have. And the key thing about the number of equations that a solution can have is there's only three types or three values that could come out of this. We can either have an equation that has just one answer. It'd be the only answer that could ever make the equation true. We could have all solutions making the equation true, meaning no matter what I want for the variable or no matter what answer I plug in for the variable, it always comes out with the true outcome, or no solution, meaning that the equation is unsolvable. To do this lesson, I actually want to go a little bit backwards. I want to start with the end in mind and talk about each of these really quick. When we talk about one solution, we're talking about a couple of things. First off, what we're doing, an equation is a statement that has two expressions that have an equal value, meaning that when we talk about an equation, we're comparing those two expressions to each other. In each of those expressions, what we'll see is a term or multiple terms that are on either side of the equal sign. In this case, we are looking at this equation, 2 times x is equal to 6. If I were to use 3 for x, that would make this statement true because 2 times 3 is 6. However, if I used 4 for x, that would make the equation false because 2 times 4 is 8, not 6. So what that means is that the equation 2 times x equals 6 has one and only one solution. The only way to make this true is to use the value of 3 for the value of x. We can see that in a lot of other places. As we solve equations, I wanted to point out this. One of the things that we can look at is in either expression, when the coefficients are different, that's a dead giveaway that we have a one solution problem. Right here, you see that the coefficient of x is only on one side. That means there's not one on the other side. That's a giveaway that this is one solution. If you have 2 times x plus 3 is equal to 3 times x plus 1, notice that these coefficients of x are different. That's a guarantee that we have one solution. Now that is to say, what happens if we have the same coefficients? So what if this was 2x and this was 2x? Then we need to start thinking about two other possibilities. We're thinking that any value for x could become true, or no values of x will make the equation true. The first one we talked about is that some equations are true no matter what the value of the variable is. For example, 2 times x is the same thing as x plus x. We know that when we simplify that, that's the same thing as 2 times x times, or is equal to 2 times x. They have the exact same value, which means that no matter what value we plug in for x, or we substitute for x, it will always be doubled and it will always be equal because we are always plugging in the same value in both expressions and always doubling it. Another example might be like 2 times x plus 1 is equal to 2 times x plus 1. Notice that the coefficients of x are exactly the same, and then we are increasing that term by the exact same amount. Perhaps you have something like this. Maybe we're talking 4 times x plus 2 is equal to twice the value or twice the sum of 2 times x plus 1. By the distributive property, this value right here would become 4 times x, and 2 times 1 would become 2, making this expression exactly the same as the expression on the left. This would be another example of infinitely many solutions. The final type of solutions that we have are no solutions, meaning that there is absolutely no way that this equation could ever become true, no matter what value we substitute for x. In this case, we see that x is equal to x, and by itself, that would be an infinite number of solutions, but you'll notice that the expression on the right has one more than the expression on the left. What that means is that this expression on the left will forever and always be greater than the expression on the, or less than the expression on the right. They can never be equal. So one of the ways that we can always look at that is we see the exact same coefficients of x. In this case, we have 1 and 1, but then the constant values are different. The constant value on this side would actually be 0, and we see 0 and 1 here. Another example of this might be, perhaps we say negative 3 times x plus 1 is equal to 4 minus 3 times x. The coefficient here is a minus 3 and a minus 3 times the exact same variable, but we notice our constants are 1 and 4. These have a different value. Now, perhaps somebody's trying to trick us and they want to use some distributive property. Maybe we'll say 4 times x minus 3 is equal to 2 times 2x plus 3. There's really nothing about this that's going to help us out because I see a plus 3 here. Even if that showed minus 3, maybe it's not the best example. Let's try this one. Let's do 4 times x minus 6 is equal to 2 times 2 times x plus 3. When we simplify this, we know that this is going to come out with 6, but the idea is that will look like this. 4 times x plus 6. We notice that the constant or the coefficients are exactly the same, but the constants, don't be fooled. This is a minus 6 and this is a plus 6. Different, so there is no solution that will ever work for this one. We see that example here in one more way, that when we solve an equation, we can completely eliminate the variables. And then when we're down to just comparing the constant values, we'll notice that the constant values will not be equal, meaning that it's a false statement and there's no solution possible. Right. So let's go back to the beginning and start applying this. First off, which one doesn't belong? When I think about these ones, I think about looking at the 4 of them. I see in number 1, this is the only one with addition, so I'm going to kick it out. Number 2, this is the only one with multiplication, so I'm going to kick that one out. This one right here is different. We're missing a 5 from this side of the equation. We're also missing a 7, but this is the solution to 7 minus 5, so this one is the only one that's been simplified. And then number 4, I'm going to kick that one out because it's the only one that's false. This one has -2 is equal to +2, which is a false statement. So come up with your own ideas and decide. Thinking about what we had in mind or what we were doing, so this next one, we're going to look at these 8 equations and we're going to classify them as true for all values or infinite solutions, true for no values, no solution. And the way that we will do that is comparing the expressions to see if they are equal or if they have the potential to be equal. We will be using infinite. We will be labeling I for infinite values or infinite solutions, and we will use N for no solutions. All right, looking at our first one, if N is equal to N, that's always going to be true because they're the exact same. No matter what we plug in there, this will be infinite solutions. The next one, 2 times t plus 6 is equal to twice the value of the sum of t and 3. Let's simplify that to see that we have 2 times t plus 6. And I see that my expressions are exactly the same, meaning that they have the exact same outcomes no matter what. This is also an infinitely many situation. Looking at this next one, that looks pretty good from the beginning. We see 3 times n plus 1, and we see 3 times n plus 1 over here, but we have to be really careful. We need to distribute first. Always simplify before you make a decision, because what you'll notice here is that after simplifying, we notice that the constant values are not equal to each other. If I eliminate the 3n from both sides, then I have that statement of 3 is equal to 1. This is a false statement. It will forever be false. There is no way this equation can ever be solved. So this one has no solutions, N. The next one, again, we want to simplify, and let's see what happens. 1/4 of 20 times d is 5 times d. 1/4 of 4 is 1. And we're left with this situation where we have 5d on the right, 5d on the left, but the left side is always 1 greater than the right side. It's impossible for this side to be equal to this side because this side has 1 greater, the left side has 1 greater. This one has no solution. We'll call it no sol. That might make a little more sense. And then we'll just call this one infinite. Looking at the next one, a little bit longer expressions, but I do see constants in here and constants in here. We need to combine the like terms, which means that they can't have, like in this case, there's no variable attached to it, where there's a variable here. This is a product I don't know, so I can't combine that with values that I do know. 5 minus 9 is a minus 4 plus 3 times x. And a minus 10 or a negative 10 plus 6 is also a minus 4 or a negative 4 plus 3 times x. And after simplifying, I noticed that these two expressions are exactly the same values. Sorry about that. So we know that this is infinitely many solutions. Looking at the next one, remember how I talked about in our summary that when we see the same coefficients and the same constants, we have infinitely many solutions. But when we say the same coefficients with a different constant, we have no solution. The first thing that jumps out to me is that I have an x on both sides, which means that those two values are exactly the same. But if I take away the x here on the left and the x on the right, then I'm comparing 1/2 to 1/3, which I know that 1/2 and 1/3 are not equal to each other, meaning that this is a no solution. This next one here, we have a little bit of simplifying we can do. -6 times -3 is positive 18. Times y, we traditionally write the coefficient first, followed by the variable. And then over here we have 2 times 9 is 18 times y. We see the exact same expressions, meaning that no matter what I plug in for y, I will get infinitely many solutions. The last one, a value times our value plus 2 and a value minus 2. That won't ever come up the exact same either, is never going to be equal either, because this expression over here on the right will always be increasing by 2, where the expression on the left will always be decreasing by 2, which means that we really don't have equality, and we can never have equality. This is no solution. Again, we can take a look at the variables, and if we eliminate the variables, we're comparing a +2 to a -2, which is never, ever going to be true. All right, let's move to the second part of this. So number 1, these are a few things that I wrote about it. True for all values, infinite solutions. Any number will work as a solution. The equation is always true, no matter what we plug in. When we're talking about true for no values, meaning no solutions, no number will work as a solution. The equation is always and forever false. So let's see some examples here. We're actually going to write our own examples. Write the other side of this equation so that the equation is true for all values of u, meaning we need this expression to have an exactly equal expression on the other side. The way that I think that we can do this, or the very first way I think of, is just to simplify this expression here on the left. To simplify the expression here on the left, we do the distributive property, 6 times u minus 6 times a minus 2, which is a minus 12, plus 2. And I can combine these two together to make a minus 10. So then I have 6 times u minus 10. If I really wanted to get creative, I could actually factor that out and say that 6 times the difference of u and 2 plus 2 is equal to a common factor between 6 and 10 is 2. So I'm going to factor that 2 out there. 6u divided by 2 is 3u. 10 divided by 2 is 5 minus 5. And even though they don't really look alike, this can be simplified. They can both be simplified to match each other. All right, likewise down here on this one is that we had 6 times u. Let's just go ahead and simplify this so we can look at it a little differently. 6 times u minus 10 is equal to, we look back at our strategy here for no values of u, meaning no solution. And what we can think of is this. I have to have the same coefficients, but I have to have different constants. So a couple of options that I could do, I could just do 6 times u. And that would work because the expression on the left would always be 10 less than the one on the right. I could do 6 times u minus 10 is equal to 6 times u plus 10, and that would be different. I could have 6 times u minus 1, and it would be different. And these are all values that would show that there's no solution possible here. Are you ready for more? Consecutive numbers follow one right after the other. For example, 3 consecutive integers would be like 17, 18, 19. Another example would be -100, -99, -98. The question says, how many sets of 2 or more consecutive positive integers can be added to obtain a sum of 100. So when we talk about this, we're talking about two numbers that could be added together in a row. So like 48 plus 49 equals 97. That doesn't equal 100, but it's two consecutive integers. It's close, but it doesn't work. What I want you to do is how many sets of two or more consecutive positive integers can you come up with that would give a sum of 100? Go ahead, they'll see a Google form that is for that, adding in whatever sums or whatever strings of consecutive integers, positive integers that you can make. So let's look at these equations. We're going to complete each equation so that it is true for all values of x. So we are looking for an infinite number of solutions. That means that we have to make our expression here on the right exactly like our expression on the left. Take a look at what we did. 3 has been factored out of the 3x and the 6. I know it's been factored because I've separated with parentheses that 3 away. So when we think about that, 3x divided by 3 is just x, and 6 divided by 3 is 2. The only value that I can possibly use in this situation is that constant value must be 2, so that my coefficient, or excuse me, so my constant when I multiply 2 times 3 is 6. It has to be equal to it. Looking right here, let's look at what they've factored out right here. Looks like we've factored out a -1. I know that you can't see the -1 there, but it would be the exact same thing as -1 is equal to something minus x. And it looks like they went kind of tricky and they moved the x over here. So a negative times a negative is a positive. That means that my value right here has to be -2 divided by -1, which would make that +2. That would be the only value that I can use to make this infinite solutions, because then when simplified through distributive property, this expression would be exactly like this expression. Looking at the next one, this one might be just a little trickier. I see 15 times x minus 10 divided by 5 is equal to something minus 2. Let's see. I know that I can simplify this first before I freak out about a fraction. Let's just look. 15 times x divided by 5 is 3 times x. And a minus 10 divided by 5 is a minus 2. Well, that's it. 3 times x has to fill in that blank so that I know that this expression is exactly like this expression. And I know this expression is exactly like this expression because under division, I got that expression. So there we go. Number 2, complete each equation so that it is true for no values of x, meaning we want no solution. Let's go as a reminder that under no solution, the coefficient has to be exactly the same, but the constant has to be equal or can't be equal. And in this case, what we knew before is I could only use 2 to make infinite solutions. So right here, I can use anything except 2. So I can use any number I want there, as long as I don't use 2. If I use 2, then I have infinite solutions. As long as I use a different one, I have no solutions. So use anything you want right there except for 2. Let's look at the next one. Before, we knew that I could use anything I wanted, or before for infinite solutions, right here I had to use positive 2. So again, in this case, use anything except, let's go except for 2. So again, I can't use 2 right there, but I can use any other number I want. Looking in right here, how do I make this one work? This one's a little trickier. Based on what we had before, we said 3x is what made it infinitely many solutions. But the problem is, in order to make this infinitely many solutions, or no solutions, I have to have the same coefficient, because I have to be able to eliminate that x completely and have a false statement with whatever's left over. If I put in the 3x right here, then that's the exact same thing. So I have to think about how can I change the constant value. Maybe what I can do is just say 3x plus 1 for this blank. Or I could say 3 times x minus 1. I can use anything I want right there as long as I don't use just simply 3x. I have to add more to it. I have to take away something from it. I have to change the constant value. So I have to do something that will change the constant value while still including the 3x. So we would include 3x, but we have to change the constant somehow. Okay, so describe how you know whether an equation will be true for all values of x or true for all values of y. Well, when we're talking about true for all values of x, it is always true because what we find out is that an equation will always come out true. I think one of the pieces that we can look at for this last question right here is if we understand that we have same coefficients and same constants, then we have the exact same two expressions. The expressions are always equal. If we have same coefficients and different constants, then the expressions will never be equal to each other, and we can know the difference between infinite solutions and no solutions. So take a few minutes, please, to go back through the summary again, review the notes that I've added in here. Please add them to your own notes and continue to review over these pieces. Let me know if you have any questions. Keep going. You're doing great. Don't you dare give up. Take care.